All right, let's dive into an idea so profoundly weird, it gave even Albert Einstein a headache. We're talking about quantum entanglement, this bizarre connection between particles that seems to just ignore the rules of space and time as we know them. Spooky action at a distance. Yeah, that's what Einstein famously called it. And honestly, you can't find a better description for the mystery here. You see, he was a huge skeptic of this whole idea because it felt like it just completely defied the fundamental laws of the universe that he himself had helped. Right. I mean, think about that for a second. It sounds like pure science fiction, right? But this very question is not just a fun thought experiment. It's right at the heart of quantum mechanics. It's a concept that really forces us to question everything we think we know about reality. Okay, so let's dig into why this was such a massive problem, not just for the physics of the time, but for Einstein personally. This wasn't some small academic disagreement. This was a fundamental clash of worldviews. So, what does that actually mean? Well, the key idea is that these particles stop being two separate things and become a single inseparable system. Think about it like you have two coins that are magically linked. If one lands on heads, the other one must instantly become tails, even if it's on the other side of the planet. They're not two coins anymore, they're two halves of one whole. And this right here, this is the core of the whole debate. Einstein's view, which he called local realism, was pretty intuitive. He used the analogy of socks. If you have two different colored socks and put one in each of two boxes and mail them to opposite ends of the earth, when you open one and see it's pink, you instantly know the other one isn't. But the information was always there. The quantum view, on the other hand, is way, way stranger. It says the particle's property, like its spin, literally doesn't exist until you look at it. The very act of measuring one instantly creates the state of the other. For Einstein, this instantaneous connection was a deal breaker. In 1935, he and a couple of colleagues published what's now known as the EPR paradox. They basically argued that since his own theory of relativity proved nothing can travel faster than light, this whole spooky action thing was impossible. There had to be some hidden variables, like the color of the socks, that decided the outcome from the very beginning. So for decades, this was pretty much a philosophical debate, physicists arguing back and forth. But how do you go from a debate about socks and hidden information to a real testable experiment that ends up winning a Nobel Prize? Well, this is how it happened. The real game changer was a physicist named John Bell. In 1964, he came up with a brilliant mathematical test. In simple terms, he figured out a way to measure the correlations between entangled particles. If Einstein's hidden variables were real, the results would always be below a certain number. But if quantum mechanics was right, the results would go past that limit. And, well, when the experiments were finally done, the results were undeniable. They broke the limit. Quantum mechanics was right all along. And that's why these three physicists won the Nobel Prize in 2022. Building on Bell's work, they designed and ran a series of incredibly precise experiments, closing one loophole after another until they had proven beyond a shadow of a doubt that Einstein's spooky action was very, very real. Okay, so this leads to the obvious question. If the connection is instant, can we use it to build a faster than light communicator? It's a great thought, but sadly no. You see, even though the correlation is instant, the outcome of any single measurement on your end is completely random. You can't force your particle to be spin up to send a 1 or spin down to send a 0. The universe is still playing by the rules. No breaking the cosmic speed limit. So if we can't send instant messages, you might be wondering what's the big deal? Well, it turns out that all this weirdness is the secret ingredient for some truly revolutionary technologies. Let's see how we're putting it to work. First up, quantum computing. Your computer uses bits, either a 1 or a 0. Quantum computers use qubits, which can be both at the same time. But the real magic happens when you entangle them. They become this incredibly powerful interconnected web. An operation on just one qubit affects the whole system, letting them solve certain problems millions of times faster than any classical supercomputer ever could. Then there's quantum cryptography, which is basically unhackable communication. Imagine you and a friend share a secret key made of entangled particles. If a spy tries to intercept and measure that key, the very act of looking at it breaks the entanglement. It's like a self-destructing message. The connection collapses and you both instantly know your channel is compromised. And yes, there's even quantum teleportation. Now, hold on, we're not talking beam me up, Scotty. We can't teleport people or objects. But what we can do is teleport information. By using an entangled pair, you can transfer the exact quantum state of a particle from one place to another instantly. This is a foundational building block for a future quantum internet. Now, for the longest time, all of this amazing stuff seemed like it was decades away, mostly because of one giant practical problem that seemed almost impossible to solve. And that problem is temperature. We're talking about nearly absolute zero, a temperature colder than the deepest parts of outer space. You see, these quantum states are incredibly fragile. The slightest bit of heat or vibration from the outside world can destroy the entanglement. So for years, quantum experiments required these massive, complex, and super expensive refrigerators. But recently, a breakthrough from researchers at Stanford has completely changed the game. They figured out how to create and maintain stable quantum entanglement at room temperature. No supercooling required. So how'd they do it? They created this tiny device using a special ultra-thin material that's amazing in interacting with light. They then used something called twisted light to create a stable, entangled connection between particles of light and electrons, and it just works right there on a lab bench. This is a huge step towards making quantum components that are cheap, energy efficient, and small enough to be practical. So what's the ultimate vision here? Well, it's to eventually embed this kind of quantum technology into the devices we use every day. Imagine having the power of a quantum computer or the security of quantum cryptography right there in your cell phone. We're still a ways off for sure, but this breakthrough makes that future feel a whole lot closer. So think about it, we've gone from a philosophical paradox that bothered Einstein to a real technology being built in labs today. It really shows that sometimes the deepest, weirdest mysteries of the universe are the ones that hold the keys to our future. We've proved the spooky is real. The only question now is, what else will it help us unlock?